Good morning, everyone. Apologies for not being there in person. I was really looking forwards to coming up to Wagga. My name's Paul Umina. I work at Cesar Australia and the University of Melbourne. And today I'm going to talk about insecticide resistance in the Australian grains industry. What I'd like to do is just provide a high-level overview of the current status of insecticide resistance in a number of grains pests, talk about some of the reasons that we're in this position, delve a little bit more deeply into a couple of species that we work on quite a bit down here in Melbourne, and then finish with a few tips and takeaways. Obviously, in the grains industry, we manage and deal with a pretty large number of insect and invertebrate species. A number of these species have evolved insecticide resistance. This includes things like the silverleaf whitefly, western flower thrips, onion thrips, and two-spotted mites. But I guess we typically consider these to be relatively minor pests of the grains industry, at least at a national level. But of course, we also have insecticide resistance in some really major and very economically damaging species. This includes the green peach aphid, red-legged earth mites, diamondback moth, and Helicoverpa armidra, also known as the cotton bollworm. And I guess we can add to this more recently, fall armyworm, which has come into the country with a number of resistances already. So I guess, to some extent, it's useful to understand which are the species that we, I guess, have to think about from a resistance perspective, but probably much more relevant and certainly I think much more practical is what are the specific resistances that we have in each of these species. And until quite recently, we didn't quite know, I guess, what that actually picture looked like at a national level. 3 or 4 years ago, Josh Thayer, who will be talking later today, undertook, I guess, a pretty extensive exercise to compile all the insecticide resistance data and reports from Australia across all of these species except fall armyworm, which at that stage hadn't actually entered the country. And this is, I guess, one of the images from Josh's work. And I think, the point I really want to make here, and I think is pretty obvious when you look at this, is that in every case, we have multiple resistances that have evolved in each of these species. And in fact, for some species, like the two-spotted mite, we have resistance to 13 different chemical groups. If we look at diamondback moth, that's a species that in Australia has resistance to 7 different chemical groups. And silverleaf whitefly, as another example, has resistance to 11 different mode of actions in Australia. And so I think this really demonstrates that not only do we have a number of species with insecticide resistance in Australia, but each one of these species has evolved multiple resistances, which I think really illustrates some of the challenges that we have when trying to manage these species using chemicals, which are still to this day the main way in which we manage invertebrate pests in the grains industry. If we look a little bit more specifically at those 4 major species, diamondback moth, green peach aphid, cotton bollworm, and red-legged earth mite. As mentioned before, Josh undertook this work 3 or 4 years ago. And since that time, which really is not particularly long when you start to consider, I guess, evolution and what we would typically consider an evolutionary timescale, we've actually started to hear about reports of resistance, at least in WA, to group 5 chemicals. And also more recently, we've had resistance evolve in diamondback moth to group 28 chemicals, firstly in Queensland, but now popping up in other states. Also, since this work by Josh, we've had resistance evolve to group 4C chemistries in the green peach aphid. And just recently, we've identified resistance to group 23 chemistries in green peach aphids. Lisa Bird's going to be talking about cotton bollworm later, so I won't talk about that here. At least the good news when we look at these 4 species is that in the case of red-legged earth mites, we haven't seen in the last 3 or 4 years this species evolve resistance to any new chemical groups. However, I will talk about what we have found in this particular species a little later on. I think what this really demonstrates is the fact that resistance is very much a dynamic process. It doesn't stand still, and these species are going to continue to evolve new resistances if we don't really mix up and rethink the way in which we're currently using chemicals. And I think another way in which I can really make this point is just in the last couple of years, we've also seen resistance evolve in a new species altogether, that being the blue-green aphid, a species and a pest of pulse crops, but also lucerne and pasture-based industries as well. And we've already got resistance now in South Australia and New South Wales to a number of different insecticide groups. Again, just really illustrating the fact that we're seeing more and more resistances pop up almost annually in the grains industry. So why are we here? How did we get to this position? No different to herbicide resistance and to fungicide resistance. The reasons are, multiple, and they're not straightforward. They're complex. There are a number of different elements that will drive resistance in invertebrates. But I think there are a couple of really important elements of the grains industry that I really just wanted to mention here today. For me, the number one, or at least the most important reason why I believe we are grappling with the resistance issues that we are today is because we are heavily reliant on broad spectrum chemicals. Again, a few years ago, we set about looking at insecticide usage in the grains industry in Australia. And this is, I guess, the data that we were able to extract. So in these pie charts, particularly the top 2 and the one on the bottom left, we can actually see the breakdown of different insecticide groups that are being used in Australia in cereals, in legumes or pulses, and in canola. What we see here is that in each of these different grain systems, we are largely reliant on synthetic pyrethroids, organophosphates, and neonicotinoids. If we contrast that to some of our other agricultural commodities, so if you look at the pie chart in the bottom right, while of course these 3 chemical groups are still largely the most dominant species, chemicals, we also see that we're using a whole variety of other different chemical modes of action when we start to consider all agricultural commodities nationally. So we've got much more diversity in these other systems than we do in the grains industry. And as I said, I think this is a real challenge for us currently. I think one of the other real challenges that we face is the widespread use of insecticide seed dressings. I certainly put a lot of value on insecticide seed dressings. I think they provide a really important and in many cases critical role in pest management in the grains industry. But one of the real challenges that we face at the moment is that all of our seed dressings that are currently available in the grains industry are underpinned by neonicotinoids. So a single chemical group underpins all of the insecticide seed dressings that are basically currently used in the grains industry. This map here basically shows what we understand to be the neonicotinoid usage across Australia. Not just here seed dressings, and certainly not just here in the grains industry, but across all agricultural industries. What we can see quite clearly is in our main grain growing regions, there's a lot of neonicotinoids being used. And I think this is really driving a lot of selection for new resistances to this chemical. These are species that we work on quite a bit down here in Melbourne, the red-legged earth mite and the green peach aphid. So let's start with the red-legged earth mite. The red-legged earth mite first evolved resistance about 15 years ago in Western Australia. And this was discovered after responding to chemical control failures that were being observed in a canola field when that particular grower was using synthetic pyrethroids. Since that time, we've been working with collaborators, particularly DPIRD and CSIRO, to monitor the distribution and frequency of resistance in red-legged earth mite populations nationally. This map basically just illustrates, I guess, our findings over the last 10 to 15 years. The red circles here indicate where we've identified resistance to pyrethroid chemicals in this particular species. What you can see is that resistance is now widespread across the WA grain belt, and it is also now found in Eastern Australia. It's prevalent now in a large number of regions in South Australia. At this point in time, we do not believe there is pyrethroid resistance in red-legged earth mites in New South Wales, nor indeed in Victoria or Tasmania. But clearly, this is an evolving story, and resistances are popping up annually at new locations in South Australia and WA. In the case of red-legged earth mites, this is a species that has also recently evolved resistance to organophosphates. The first confirmed case of organophosphate resistance in red-legged earth mites was also identified in Western Australia. And again, since that time, we've been actively looking at the distribution of organophosphate resistance in this species. And again, we've got a map to illustrate the results of many years' work. Again, what we've seen is that we've got red-legged earth mites now in Western Australia across most parts of the WA grain belt with resistance to organophosphates. We've also got resistance in South Australia, and more recently, we've picked up resistance in Victoria. We've got red-legged earth mites now with resistance to organophosphates in the Wimmera, in the central region and the northern region of Victoria. We expect in the not too distant future that we'll certainly have resistance in southern New South Wales as well. And it's almost inevitable that new resistances will evolve and that this resistance will continue to spread into new regions. So this is certainly something that I think up in and around Wagga we need to be consciously aware of and keeping an eye out for, and thinking about what we can do now to minimise the risk of selecting for resistance in this species. But of course, not all resistances are built the same. This is just some data from some of our earlier work, which basically is a dose response curve where I guess we can identify whether a population or a species has in fact resistance to a particular chemical. So on the y-axis, we have mortality, and on the x-axis, we have increasing concentration of a particular chemical. So in this figure here, we're testing a synthetic pyrethroid, bifenthrin or Telstar, and this dose response curve is what we would typically see for a susceptible population. This curve here is what we saw when we tested one of our resistant populations from South Australia. What you can see is even at the very highest concentration tested, the resistant population saw no mortality whatsoever. Now, we know that this resistance is driven by something called target site resistance. And while the resistance mechanism itself is not particularly relevant necessarily to the field, what is particularly relevant is the very high level of resistance that it does confer. And so in this case, we see a resistance in the order of 100,000-fold. And this is important because what it means is that growers cannot control red-legged earth mites whatsoever when they use synthetic pyrethroids if they've got this resistance mechanism present. It doesn't matter if we use multiple applications. It doesn't matter if we increase the dose above recommended label rates. We're not going to achieve control whatsoever. In the case of organophosphates, which can be seen in this graph, the story is quite different. This is a different resistance mechanism. The important part here is that we only see fairly low level of resistance to organophosphates. And we know, because we've tested this in the field, that there is still a possibility to be able to achieve some level of control with red-legged earth mites with organophosphates, even when they have this resistance. However, it's not going to be a long-term sustainable management option. But at least in the short term, we do have some options available to us. But it is quite important that we understand which chemicals to use. So just changing tact a little bit, if we just now talk about green peach aphids, what we've identified again nationally in this particular species is that we have high levels of resistance to pyrethroid chemicals and to carbamates. So they're products like pyramor and pyramocarb. Once again, if we start to look at what we've, I guess, undertaken over the last 10 years or so with surveillance, again, red dots here indicating resistance. What you can see in the case of pyrethroids is that almost all populations that we test nationally actually have resistance to pyrethroid chemicals. And that's certainly the case in southern New South Wales. The story is very, very similar for carbamates. Almost all populations now out there in the field have high-level resistance to carbamates. In the case of green peach aphids, we also have low-level resistance that's evolved to organophosphates and also low-level resistance that's evolved to neonicotinoids. So this is a really challenging species. And again, we've been screening for these resistances. In the case of organophosphates, almost every population out there has low-level resistance. And in fact, almost every population out there has low-level neonicotinoid resistance. And we again have undertaken some work recently that would indicate that from a field perspective, this low-level resistance in green peach aphids to neonicotinoids is very likely to reduce your length of protection offered by insecticide seed dressings. So even though we've got low-level resistance here, it is potentially still quite relevant for the field. And, in the case of green peach aphids, the story doesn't end there. As I mentioned up front, we've also seen a number of new resistances pop up in the last few years. This includes resistance to transform, sulfoxaflor, where we picked up low-level resistance in a number of different populations around Esperance in WA a few years ago. And since that time, we've picked up resistance in a number of other locations, both in Western Australia, but also over here in Eastern Australia, including New South Wales. The good news, though, is that not many populations of green peach aphids out in the wild possess this new resistance mechanism, but it is certainly something to be aware of. And as I also mentioned a little while ago, we've recently picked up another resistance in green peach aphids, this time to group 23 chemistries, so things like Movento. So while Movento and other group 23 chemicals are not registered in the grains industry, once again, it does illustrate the high propensity of species like green peach aphids to evolve resistance. These are highly adaptable species, and if we continue to use chemicals, as we have been, the evidence is pretty clear that these species will unfortunately adapt and evolve, and they'll overcome those management practices that we're currently employing. So, what do we do? Well, it may seem fairly bleak. I don't really think it is. I think, having this information is really critical, and I think it's the first step in understanding what chemicals are available, what's likely to be effective. But I think what it also does, it really illustrates the need to move towards an integrated pest management framework. The only way that we can really prolong the life of insecticides is to implement and adopt integrated pest management and insecticide resistance management. They're just going to be critical to the sustainability of the grains industry moving forwards. And I just want to leave you with a few tips as we start to think about how we move towards that framework, recognising that, of course, many growers and many advisors are already making these recommendations and implementing these practices. I think the most important thing that we can do as an industry is to reduce our reliance on broad spectrum chemicals. We really want to be avoiding synthetic pyrethroids and organophosphates wherever possible. I understand that they're very cheap. They're very effective and they have a really broad pest spectrum. So I understand why we use them a lot. But of course, they're highly toxic to beneficial insects and they really limit our ability to adopt IPM. And of course, as we've seen in the case of red-legged earth mites and green peach aphids and a lot of other species that we manage in the grains industry, we've got resistances now popping up to these chemistries time and time again. So we're going to have to move away from these chemistries anyway. I'd like to suggest that we don't use insecticide seed dressings every year in every paddock. They've become really commonplace, particularly since the introduction of Russian wheat aphid a few years ago. I think, again, they're a really important tool for us. They're a tool that we don't want to lose. And again, I think we have to start to think about which are our high-risk paddocks where seed treatments should be used and which paddocks can we potentially get away without putting a seed treatment on in some years. And of course, when using chemicals, and of course, we're still going to be using chemicals to manage many of our pests, it's not just about what chemicals to choose, but it's also how do we use them much more strategically. And so, for example, and there are many examples where this can be achieved, in the case of red-legged earth mites, we've got Time Right, which is a really effective spring spray that not only provides effective control in spring, but also provides really, really good control the following autumn. My second tip is to bring some culture. Not only can we manage these species using beneficial insects and chemical controls, but there are also some non-chemical cultural control methods that we can implement for a whole variety of different grains pests. In the case of green peach aphids, as one example, we can control those weedy hosts and volunteer canolas 14 days prior to sowing a canola crop. By doing so, we drastically reduce the risk of green peach aphids infesting that canola crop during that early growth establishment period, which is a great way to minimise the risk of viruses like turnip yellows virus coming in the first place. Of course, it won't eliminate the risk, but it really reduces the risk. A very effective strategy that I don't quite think we're using enough of. In the case of red-legged earth mites, just another example where pastures are in the system. We can strategically graze these pastures to below 1.4 tonnes of food on offer in spring, and that will effectively do the same job as a Time Right chemical application. It will reduce red-legged earth mite numbers without the need to use chemicals in the first place. And of course, the best way to minimise resistance is to not use chemicals in the first place. And my third tip, and again, I'm sure you'll hear this quite a bit today, is to swap out your players. It's really important that we avoid the repeated applications of chemicals from the same mode of action group. And in the case of insecticides and miticides, do not cut rates. That's a really good way to select for resistance. So do not cut rates, please. And finally, there have been a number of resistance management strategies that have been developed by GRDC. They are available on the GRDC website. Although they are a little bit outdated, I would still encourage you to download them. We have one for the green peach aphid and the red-legged earth mite. There are some really useful recommendations, some of which I've touched on today, but some other recommendations that I think are quite practical that really strike a balance between providing profitable pest management, but also reducing that risk for further resistance evolution. Finally, I'd like to just finish with acknowledgements. There are a number of different people and organisations that have contributed to our work over the last decade or so. In particular, I'd just like to acknowledge GRDC, who have funded a lot of our green peach aphid and red-legged earth mite insecticide resistance surveillance work. Thank you.